This is a follow-up to the calculating limited infinity calculation video, and I want to justify this cover-up method, where we just cover up the non-leading terms. One big warning, okay, right here. Cover-up only should be used, it only is guaranteed to work for polynomials and rational functions. Watch out especially for square roots. And there's weird signs that come in there. Okay? And I've got some other videos about those tricky examples. But right now I just want to emphasize the more basic examples with rational functions and polynomials. Okay, so here was the deal. The claim was that this equals just something very simple. Okay? And I want to just show how a little bit of algebra actually justifies this much more carefully, together with this basic building block and the limit laws. Okay, so the idea here is that usually 1 over x we think of as a more complicated gadget than like x. Okay, but I want to just maybe just right in here, let me just add one more building block. The two building blocks we're going to use is that the limit of 1 over x is 0. The nice thing is that's a number. The limit of x or x to the n is not a number, it's infinity, where n is like some number that's bigger than 0. So the thing is, we can't do algebra with infinities. So it'd be tempting to just use the limit laws to take a limit like this and just pull it apart. Limit of the quotient is the quotient of the limits, limit of the sum and difference, all that. But as soon as we do that, we start pulling it apart and we discover the building blocks are mostly infinities. Like this is going to infinity, this is going to minus infinity, this is going to plus infinity. It doesn't work. So we do a little algebra, a little unfamiliar algebra, to get it to where we start talking about 1 over x instead of x or x to the n. Okay, so let me insert it up here. What we do is we're going to recopy this guy. I'm going to put the rest of it on separate lines. Okay. And I'm just going to multiply the top and bottom by 1 over x cubed. Okay. And let me see what that does. So let me insert another line in here. I'm just going to distribute that 1 over x cubed through everything. So 5x cubed over x cubed is just going to be a 5. Minus 37x, well, x over x cubed, that turns this into a 1 over x squared. And then the 200 over x cubed, that's going to turn this into this guy. So I've taken care of that guy. Again, distributing through a 1 over x cubed, that's going to turn this into a number. It's going to turn this into x over x cubed, or 1 over x squared. And it's going to turn this into 77 over x cubed. This looks like backwards progress. My goodness, I took this perfectly nice thing with polynomials and I made it a fraction, a compound fraction. This is usually not the direction that we consider simplification. But look at what happens. Now, I'm going to try limit of the quotient as the quotient of the limits, hoping that the top and the bottom are going to go to just numbers and have limits. And then I'm going to try limit of the sum or difference as the sum of the difference. And so I'm just going to break it up into the individual pieces. If the individual pieces all go to numbers, then I'm good. 5, certainly good. 1 over x squared, aha. That's just our basic building block limit times itself. And that's going to 0. So this guy is going to die. 200 over x cubed, that guy's going to die. 12 over x squared, that guy's going to die. Minus 77 over x cubed, any of these guys is going to die. And so it's just the limit of 5 over 15. Oh, it's just 5 over 15. We're done. Okay. So what's happening is we can just basically scratch off these guys, scratch off this guy, scratch off this guy. Just say that they all go to 0. Whoops, I didn't want to do that. They all go to 0, and what's left is here. And guess what? That's exactly what we had to begin with as our shortcut method. And what happened is that all these guys died because when I look at a lower power of x and I divide it by x cubed, it turns into something with an x in the denominator and they all die. So that's a careful justification. If somebody wants you to write out, like on an AP free response, how did you know this limit, this is really the kind of thing you're going to need to do. What about when I have the power on the bottom is bigger? Okay, well, we can do the same exact thing. we can do, take this guy. Now what do we want to multiply it by? It's kind of a little unclear which power to use. If you always use the power in the denominator, it's best. So this, I'm still going to use a cube here, okay? Because the denominator we'd like to make more simple. Denominators of fractions are more dangerous. We'd like to make that be more simple. So 1 over x cubed, okay? What's that guy going to turn this denominator into? It's going to turn it into 15. That's a number, which is good. Plus 12 times 1 over x squared minus 77 over x cubed, just like before. And up here, it's going to be very similar, except what is this going to turn into? Ah, now this is a 5 times 1 over x. And then the rest of it's going to be exactly the same. Let me just pick it up from here. Aha. Now, the bottom is still going to 15. Because this guy is going to die. This guy is going to die. These are all dying, including the top one. So it's 0, 0, 0 over 15, and we just get 0. So this is why when the denominator power is bigger, you're always going to die, because you can just make this into just stuff with numbers that's not going to 0 by dividing by this power, x to this power, the leading coefficient of the denominator, a leading power of the denominator. And because this power is bigger than this guy, it's going to kill these off all separately. Okay. So, the other two examples. What about this one? Very similar, but now we actually get infinities coming in. Okay. Here, we're going to multiply by 1 over x cubed again. It's always the power of the denominator is the best one to use. The bottom, oh, I could just copy that. It's the same exact thing I got both times here. This is not changing. Okay. And let's see, let's just delete that. That's not going to be relevant. I claim we're going to get infinity, but let's see. Let's put a question mark. Do we still get infinity? Okay. So what are we getting on top? Aha. We're getting almost the same thing, but let me just copy it and change it. Now it's a 5x on the top. Okay, so now what's going on? Almost exactly the same. This is going to a number. 0, 0, 0, 0. Those can be ignored. So what are we getting? We're getting just 5x over 15. These guys, because they're going to 0, they really, really, really can be ignored. And because the bottom is just a number, it's fine. The only thing that's a little weird is the top's going to infinity. But if I take something going to infinity and add zeros or subtract zeros and then I divide by 15, it's still going to go to infinity. Okay. Similarly for this one, although I don't think we need to bother with that one. And with this one, I got a little messed up last video with numerics because I think these numbers were just a little too big. But here we can actually now really we can really verify that this is really going to infinity because, okay, let's just delete that. I can still do the same thing, but it's just a little bit different. I'm just going to factor out the leading term. Division is the same thing as factoring, really. Oh, let me just copy it. So it's the same thing in disguise. I'm going to take the x cubed, I'm just going to factor it out. And so this is going to be, I'll put in parentheses. This guy is going to be in parentheses. I've factored out an x cubed, so that's just a number. This guy turns into a 1 over x. When I factor out an x cubed, it's essentially doing exactly what I was doing on the top and bottom here, just dividing by x cubed. Here, because it was a fraction, I could do the same thing to the top and bottom and have no effect. Here, I actually have to express it as a factor. But now what's going on? This guy's going to 0. It just goes away. This guy is going to a perfectly nice number, and it's a positive number. And so I get the limit of positive times x cubed as x goes to positive infinity, and that's going to be infinity. Okay, so these are the careful justifications of this cover-up method. And this is always going to work when we have polynomials and rational functions. The lower order terms just don't matter. But if you have things like square roots, it actually is rather more subtle. And in particular, there's some weird sign issues and some other subtleties that happen. But I wanted to focus on the simple ones here.